Welcome to example number 8. There are a lot of common applications for the continuity equation. So one of the common examples would be a garden hose or a fire hose, and what happens when you obstruct the opening. So in example number 8, we have a unobstructed area of 2.85 to the power of negative 4 meters squared, which fills a bucket in 30 seconds. So we'll draw a little bucket here, and a time of 30 seconds. And the volume of this bucket is 8 to the power of negative 3 meters cubed. And we'll use a capital V here to represent the volume. We're asked to find out how fast the water is leaving the hose. So this will use a small letter V or a script V to figure out that velocity. Just notice that I've distinguished between my two V's here. Since the density of the fluid, water, is incompressible and is constant, the volume flow rate past any particular point, either whether it's like this, whether it's unobstructed or obstructed, will be the same. The volume flow rate is calculated by taking the change in volume divided by the time that it takes to fill the bucket, for example. So if we take the volume of the bucket of 8 to the power of negative 3 meters cubed and divide by the time it fills it at, which is 30 seconds, we can find out the volume flow rate, which gives us an answer of 2.67 to the power of negative 4 meters cubed per second. So that is the amount of fluid that it takes, or the amount of volume per second. Now R can be calculated as well. That volume flow rate can be calculated by taking the cross-sectional area A multiplied by the velocity. We'll use area 1 and velocity 1. So we now know the rate of flow, which is 2.67, and we also know the cross-sectional area, therefore we can find the velocity. So velocity 1 will be that rate of flow divided by the cross-sectional area. So that is 2.67 to the power of negative 4 meters cubed per second divided by the area, which is given as 2.85 to the power of negative 4 meters squared. And hopefully you can see that the units cancel out, meters squared here, and here you'll be left with just a meter. And so you'll have units of meters per second. And this gets you a velocity of 0.936 meters per second. So there's part A. Okay, part B. Find the velocity if you were to obstruct the opening by reducing the radius by half. So part B, the new radius R2 is 1/2 of the original radius R1. So hopefully you'll realize that as the water moves past your thumb, where the cross-sectional area is now smaller, forming a very fast speed v2. So velocity 2 is going to be much faster than the original velocity 1 because you've reduced the cross-sectional area by increasing the velocity. Okay, now there are a couple ways of doing this. We know that the rate of flow remains constant regardless in both scenarios. So really, the product of these two must be constant. So if you were to decrease the area, then the velocity has to increase. So let's find out what happens to the area. Area 2 is equal to pi r2 squared. We're assuming this is a circle here. Now, R2 is half of R1. So if we plug that into here, we'll have 1/2 of R1 squared. That's going to give you, when you square the half, you'll get a quarter of pi R1 squared. So the area of 2 is 1/4 of the original area, area 1, which is 2.85 to the power of negative 4 meters squared. That's going to give you a new area of 7.125 to the power of negative 5 meters squared. So now you know the area 2, and you have the rate of flow, which remains constant. You can find the new velocity. Velocity 2 would be the rate of flow divided by area 2. The rate of flow is 7.125 to the power of negative 5 meters squared divided by r, which is 2.67 times 10 to the power negative 4 meters cubed per second. And I just realized that these should be flipped. And there you go, I've just flipped them, and you get, actually, when you divide these out, you should get 3.74 meters per second. Now, you probably didn't need to really go through all this. You could just answer this sort of conceptually, meaning you could say that since R2 is half of R1, then A2 would be a quarter of A1. Why? Since area is proportional to R squared. And then you could say, well, if you quarter the area, then velocity 2 will be 4 times velocity 1. So you could just really take this answer that you had originally of 0.936 and multiply it by 4, and you get the same answer, 3.74 meters per second. And the reasoning for that is that the area times the velocity is constant by the continuity equation. So as you reduce the cross-sectional area, you increase the velocity of the fluid. And that's it for example number 8.